This talk was about the food. We are thinking in the luxury, to have more, and that is not sustainable. We need to use what we have. It's all what you need to be happy and to be comfortable.
This is our composting facility, our organic waste recycling facility. It's a great way for KAUST to become more sustainable and getting closer to a zero waste KAUST.
Resilience is when life hits you really hard, that you get back up.
Resilience is bouncing back. It's about never give up and keep moving forward.
Hi, good afternoon, everyone. Welcome to the second week of the Winter Enrichment Program 2022 for KAUST, for the in-person and online attendees today. My name is Daria Baran, and I'm the co-chair of WEP this year. And I hope you enjoyed some breeze and rain for the ones in KAUST this weekend, which was an exciting event for Saudi Arabia. So today we have a special guest, Professor Paulo Esteves-Veríssimo, as our keynote speaker, and I'd like to introduce him with a couple of sentences. Professor Veríssimo has been a professor at KAUST and the director of the Resilient Computing and Cybersecurity Center since November 2022, and he joined us in very important times. Before KAUST, he had been a professor and FNR Pearl Chair at the University of Luxembourg, FSTM, as well as head of Critics Research Lab at the SNT Center at the same university. Critics has achieved world-class results and endured the capacity of research in resilient computing, cybersecurity, and dependability. He had also been a professor at the University of Lisbon, Portugal, and a board member at the same university. There, he created the Navigators Research Group and later became the founder director, a computer science and engineering lab whose research in cutting-edge areas has consistently been backed by key indicators of excellence until today. Professor Veríssimo was the representative of UNILU SNT in the European Cybersecurity Organization and a member of its scientific and technical committee, as well as chair of the IFIP on dependable computing and fault tolerance, and their vice chair of the steering committee of IEEE of IFIP DSN conference. He is a fellow of the IEEE and ACM and an associate editor of IEEE Transactions on Emerging Topics in Computing. So please join me welcoming Professor Veríssimo to our stage.
Thank you very much. Good morning all, or should I say good afternoon, and to those of you who are here and those who are on the remote. I hope I will be able to fill in this time with interesting thoughts about a very special facet, a very important one of resilience, which is the digital resilience, and how it relates to what we have known and seen on the news about the problems of cybersecurity and safety and all that. The center that I'm directing here, actually it just celebrated the first year, has, I would say, a quite interesting mission, because my DNA tells me that whatever I do can be a theory, a theorem, if you want, has to have a practical application. So the mission of the center, and this is something that all the professors who are already in the center are united around it, is to create, long-term scientific research capacity, but one that is translational. I'll tell you what the word means. The word means that whatever you're going to study and research might have an application. It could be a startup of yours, or if you go to a company, to try to bring that company to new heights. And actually, it's the second point, induce in the region technological and societal transformation. And with this, these are key elements to achieve something that a lot of countries are looking for, which is digital sovereignty. of the kingdom. Of course, that's what I'm talking about. That's the mission of the center. And of course, it will come from top-level research and then get this translation, if you want, to the real world. Now, I've been saying, and some of us in the world, you know, some groups were pioneers, I would say, of this, that resilience is the cybersecurity of the 21st century. It looks like, wow, you know, it looks like, you know, something you could tweet, right? But actually, the reason is that cybersecurity paradigms, the ones we have them, are insufficient. And so we have to do something else. It's not that they're bad, they're just not up to the challenges we have in the current world. It's pretty much like if you go ask your grandparents, they would probably live in a world where the key to their door would be this very old-fashioned iron keys and all that. And that doesn't work now. Now everybody uses, you know, fishy locks or something, or electronic ones. You know, depending on the threats, we have to adapt. And so resilient computing marries, you know, bodies of knowledge of at least 3 very important points. And you know, what I'll try after this hour, if you're convinced, it's going to be great, that none of them alone solves the problem. Security, privacy against attacks, dependability, safety against accidents and catastrophes, and artificial intelligence, machine learning, deep learning against uncertainty. But none of them solves all the problems. And only all of them working together will get us to our objective. And this is what we, you know, several groups are promoting, let's see. But it's already in the agenda of countries like the US or the European Union. Now, what is the big problem, by the way? It's that the world became an immense infrastructure. What we call the cyberspace is super complex. You know, you have the utilities up there, and you have the connected cars, and you have the autonomous cars, the transportation systems, you know, rockets, and, you know, drones, and probes. You have biomedical information, super automated these days. You do genome editing and this kind of thing. And you have your home, your smart home. You could talk to your smart home from your connected car. Now, the problem is that this is all interconnected. Actually, it starts with this complex, the Internet and Cloud and Web complex. But then, you know, it gets to these fringes that we call cyber-physical systems and Internet of Things systems. Those are the ones that connect us to the real world. Those are the ones that have effects, you know, the sensors, actuators. So those are the ones that put the cars running or control the utilities. But those are the ones that can make things explode. And actually, from a smartphone today, you could go through this infrastructure and, you know, make something blow. Some of us in our teams, we know how to do that. And the idea is to prevent that at all. Now, is the world cyber secure? Because, of course, you can tell me, well, you know, but we really work, you know, things are working, except for the internet that was almost collapsing this past few days around here. Well, you know, be attentive to what you read in the news. It's a lot of stuff. So really, the cyberspace is not secure today. And it's largely because the paradigms that we use don't let us try. I mean, I think you agree with this sentence, or you would say yes to this question. You know, we don't trust websites, home banking, storage systems, private or public clouds, internet communication. We really don't trust them. We live with it, but, you know, it's always failing under our nose. And why? Because they were built around concepts that were possible when I started my career some dozens of years ago. It's based on prevention. We keep the hackers out. We safeguard the perimeter. We have good code. And all these things proved infeasible today, given the way the world has evolved. You know, it's a distributed infrastructure, yet we continue, you know, some of the auditing methods, they just tick boxes for components. This is good, this is good, this is good, etc. And it's highly exposed to threats, but, you know, we keep thinking that we can prevent attacks and we can safeguard the perimeter. We use firewalls to put the hackers out. It's not going to happen. And there's steadily increasing software vulnerabilities. I saved you a graph that is very worrying that shows that every year there are thousands, 5,000, 6,000 of new vulnerabilities in commercial code. Still, we continue thinking that, no, we clean up the code, we take the bugs out. The famous, Microsoft Tuesday updates, right? No, it's not solving the problem. Maybe it did something, 30 years ago, but not now. And there's a degradation of the threat plane. What does this mean? This means that the adversaries are every day more powerful. The part of cybersecurity and dependability and resilience that I do in my research group, I'm going to tell you a little bit about it, is more focused on this critical area, this digital, critical infrastructures. And so some people tend to say that we have this paranoid, attitude about things. No, we're simply realistic. Things happen, and the adversaries sometimes are very skilled. Yet we continue having, largely companies with human-centered ad hoc mitigation, these security operations centers where people look at graphs, see alarms, and do something. Now, the problem at today, a lot of the attacks are AI-powered, they're ML-powered. And so we have to come up with something that is much more powerful than having a human make some decision, because when it gets there, it's too late. Now, if you still think that, well, maybe it's not that bad, think about two things, one already in 17 and one very recent, that show what I'm talking about. It's a question of mentality, of the paradigms people are using. This 17 WannaCry, some of you heard about it probably, was ransomware, was the first very high-level, massive, devastating. It was about, locking a data, a data repository. So the attacker encrypts it with his own key, and then, okay, if you don't pay me a ransom, I will not decrypt it. I will not give you the key. And more recently, the way you felt very nervous, I'm sure, because Facebook went down, and with it, WhatsApp and Instagram, and suddenly you felt like orphans, right? At least some of you. Well, recently I provided an analysis of that. Actually, it's from you can find it from KAUST. It's online. If you just search the day Facebook went down, the tale of resilience. And how funny is it when I was going through, because there's documentation on the web that explains what happened, and as I was going through my presentation, it was really, obvious that if this would be a mantra for resilient computing, this is not a lecture on that sense, but if this would be the mantra, I finished my presentation by saying that the Facebook episode missed quite a few of these rules. So you see, had they designed along resilience principles, very little of what happened would have indeed happened. So you see, this makes us think, what else can be done? And actually, let me now jump to the other. I told you there are several, bodies of knowledge. Now, this is dependability safety. This is another body of knowledge. There's a lot of know-how about it. And actually, it's what makes planes fly and this kind of thing. And actually, we trust these things. We don't even think when we catch a plane, is it going to fall? I mean, they fall, but so little of that. So we don't even think. So it's about planes, trains, rockets, probes, satellites, power stations, things, control systems in the world. We trust them. And why do we trust them, my friends? Because they don't fail. They don't tend to fail, of course. And it's exactly what I said. They don't fail, and I correct. They don't tend to fail. Actually, they are. This area was where I started my career many years ago. And actually, they're based on a powerful and very humble paradigm. All that works fails. So it may surprise you, but when people start designing a plane, actually, I know some of the scientists that were behind, the body of knowledge created to today design Airbuses and Boeings. They say, well, this is going to fall if we don't do something. So, and they go about understanding what are the components that can fail so that the whole will not fail. Meaning, I don't know if you know that, but today all commercial planes can land with at least one, engine less, and some of them with even more than one engine. Actually, the rule for the quadri engines is that they can land with one engine. How amazing is that? Because they're designed exactly having that in mind. So they're not designed for a perfect thing. They're designed for something that can go wrong, and then they use, things like, if you Google these words, you understand: fault tolerance, recovery, masking, redundancy, and so on. All right, so this then would be the way that you design systems that, in inverted commas, never fail, meaning their probability of failure is very small. So dependability safety would be the way to go. I mean, it looks like, wow, why don't we, instead of classic cybersecurity techniques, we use classic dependability safety techniques? Well, actually, surprise, some years ago, several groups started, and we looked as well into that, because at that time we were, and I want to be very active here with autonomous vehicles. And actually, those very systems that would never fail, cars, for example, are largely automated. I'm not even talking about autonomous cars, I'm talking about our cars. They're largely automated. They have a lot of computers and electronics that just, controls things, to make it easy for us. Now, the beauty of the thing is that they were designed to cope with accidental problems, not hackers. And so there's a lot of hacks that have been happening over the years. So neatly, dependability safety alone would not solve the problem, because it's super good to prevent these accidental faults, but then if a hacker wants, he or she will take over the car. And actually, we did a study in 2016, we published in Vienna at a workshop of CCS, and we were explaining that the way you design these things, really, I mean, they're certified very attentively. It's that faults in a well-designed car lead to an infinitesimal and acceptable probability of catastrophic failure. You signed at the bottom, you commit your responsibility. Yes, I underline this. The problem is that this residual effects that can stay in whatever thing, can be a nuclear power station or a car, if it's about Mother Nature, yes, it's not going to happen. If it's about a hacker, we call them vulnerabilities, and actually if the hacker discovers them and accesses them, it's going to happen, not it may happen. So you see, it is also not enough. And so at this point, some years ago, we were at this crossroads. Wow, what can we do? Cybersecurity is failing on us. Dependability and safety also does not solve all the problems. Solutions are needed. And actually, when you are in this thing, every one of us, we tend to look at the first thing that goes around the corner, right? And actually, artificial intelligence, machine learning, deep learning, they have been showing a lot of promise, really. It's amazing what they have been doing for several areas. And actually, this is, you can look it up, it's so funny. This is the hype cycle of Gartner. It's a consultant firm. And actually, cybersecurity was in the hype some years ago. And the hype is at the top. And if you look it down, it's the peak of inflated expectations. So that's also what we have to be careful about. We have to be careful not to see, well, AI, ML is going to solve all the problems of the world, because then it's like spraying. We spray AI, and it's going to fix that. And actually, a lot of the things that really, have been, surprising us positively, they're not in a critical area. So one thing is making recommendations for a movie. The other thing is really preventing, planes from falling down, or preventing data centers from being hacked and ransomware and all that. So those of us who work in this area, we have been raising words of caution that yes, absolutely, AI, ML, especially deep learning to cope with new and uncertain situations, is going to play a very, very important role in this area. But we have to be careful with this circular argument, which is we will use, I'm researching that area in my group now. which is AI/ML for cybersecurity and safety. But be careful, because at the same time, we have to be sure that the methods we're using are cybersecure and safe themselves. You know, there's a Latin phrase, quid custodiet ipsus custodian, meaning who guards the guard. I'm sure you heard about that. Who guards the guard? So this recursive argument is very important. I'm just calling your attention that this will be the making of getting us into the good use of AI. Actually, on the right, we have some very worrying problems that have been happening with AI-powered algorithms used exactly as I tell. It's not a recommendation for a movie. It's a critical area where people can be killed. All right, so, you know, after that, of course, we say, okay, but do we need resilience? I mean, can we not improve these things or whatever? I remember I told you, it's them working together that gets us to new mindsets, to new paradigms, to new algorithms, to new programs. And actually, there has been research efforts in this area. This is a research network in Europe. America was probably institutionally, not in terms of research groups, the bloc that first endorsed the principle. This is a statement. This gentleman was the director of NSA and the leader of the US Cyber Command, so a person that needs to solve things for yesterday. He was saying, well, prevention is cool, but we better do resilience. And actually, Professor Bill Sanders, who's going to be a speaker also in WEP, was one of the distinguished scientists that actually were probably, you know, promoted this vision from the NSA side. I was also very honored to have been taking part in also the changing mindset in Europe. I'm just here for a year. I've been in Europe all that time, and the recent cybersecurity strategy for the next 10 years is a document that insists very heavily on resilience, and a lot of it has to do, of course, with resilient computing. Now, let me then finish my presentation with some achievements, because up to now, just telling you, oh, no, it's a great idea, you know, it's really super cool. You should definitely think about that when you're thinking what you want to do in your future. This is what has been happening. I'm going to tell you. So this is my research group in the center. And of course, it's amongst the groups that are in the center, one that bets very heavily on this strategy for research and teaching. And I told you that I've just arrived, right? So I'm going to tell you some successes that you can achieve, and I'm going to quote, as you're going to see, some research that I've done in Luxembourg. You can also reach out for that group, my name in critics, and you get there. This was a very neat thing. This was a project with Intel, the company, right? And we were tackling the autonomous vehicles area, and actually, doing two things that I want to pursue also around here, which is stating that the autonomous cars, the connected cars, but also, and very especially the autonomous cars, they need cooperation. They need to talk to each other, which is not happening. Today, they're individualistic. They have all the apparatus, radar sensor, you know, LiDAR, etc. And then collaboration is going to be important. And the other one is looking at resilience inside the car controls, you know, the so-called ECUs, electronic control units, and the car networks. I'm sure you know that there are dozens of small computers inside the car, and they connect through networks. And this one was really quite interesting project. We have just published the last paper of this effort. I was already in KAUST, and it's about this. When your car is on the road, it has to see the environment. And seeing the environment, of course, has to go around corners, right? You know, how do I see around the corner? When we're driving, we cannot do that. But cars can, exactly if they enter this new world of cooperation, but it has to be reliable and secure, resilient cooperation amongst the cars. The GPS is not going to solve all the things, okay? And so we came up with very robust and resilient algorithms that would be capable of giving you this metaphor that you're seeing everything that is happening. Of course, safeguarding privacy and all that. No, it's the conjunction of all these things that matters. And actually, to achieve this, you will have to cope with all the threats that can happen. A lot of them are accidental. I'm sure you have seen your Uber guy is already arriving, and then you look at the, your smartphone, 2 minutes later, and it comes back and forth, because, what Uber does is that they don't do any of that. They just, use very fragile algorithms. And actually, if you go to countries, I will not name the countries, but if you go to countries where communication is a bit flaky, it's amazing. The car jumps, the Uber car jumps. It's here, and now it's there, and now it's there. I mean, it's completely amazing. So I'm talking about protocols, distributed system protocols that can handle this kind of problems. The other thing was super fascinating because, my initial background is electrical engineering, electronics, digital electronics. So I still keep this bug. And so in my groups, there's always people working at this chip level and FPGAs and all this, doing these prototypes to really, this special purpose computers. And then what we came up with was, okay, so a chip today has cores. All your PCs, phones have several cores. They can have 2, 4, or they can have a lot of them. And actually the future, the present, I would say, is what we call many cores. So a chip is going to look like that, your chips regularly. It's going to have a lot of cores inside. They're going to go down in price sufficiently that this is affordable. These are called systems on a chip. Now, the problem today is that if any one of those cores fails, the whole thing fails. And so it's what you're used to. If your chip fails, it fails. So having several cores does not contribute anything to the robustness, the resilience of the chip. Now imagine that you put these little blue dots, you put, some special, special hardware so that, some of the cores can fail, but the whole doesn't fail. It's a basic, remember I told you redundancy, fault tolerance. It's a basic principle of dependability, but now used for anything. It could be attacks. The hacker could attack some of those cores, but not the rest. And these little things are super simple. And so if they're simple, we can trust that they will not fail. And if you do this, then you'll have a chip that is amazingly resilient compared to what the current chips are now. And obviously, this opens perspectives for a lot of things, but think about what I was mentioning about the cars. So suddenly now, this easy use of the cars, they don't just fail like that. They have a process of failure that goes until, only just a very few cores exist of what is there initially. And this is very promising. And this is a research that I want to continue doing around here. Now, using this principle of fault tolerance, so let's go to data centers. I don't know how much of you know about that, but today the data centers, the cloud, they sell you computing by the meter or by the kilogram if you want, because they are based on this virtual machine concept. So a virtual machine, a VM, is an illusory computer that you can buy from Amazon or whatever. And actually, it's software crafted, and it's based on a division of your hardware, of your microprocessor, by these hypervisor things called hypervisors. And they give you this illusion that these virtual machines are separated computers. Now, what happens? The world tends to forget that because it scares them, because it's kind of contradicts this principle of clouds that moves tens or hundreds of thousands of euros or dollars. But there's something called a VM jailbreak, if you look it up in cybersecurity, which is an attacker sitting on a VM can attack the hypervisor and then control the adjacent VMs. It's not very nice, right? It happens. And so some of the algorithms that I've been studying and I want to continue studying are about making this hypervisor failure-proof. It's immune against this kind of attacks. So it's also, a promising avenue. Now you see, this is a perfect example of what I was saying. This is achieving cybersecurity using dependability, fault tolerance methods. All right, so blockchain. This is probably one of the works that was more emblematic in our team in Luxembourg. I don't know, I'm sure you may have heard that have been some scams with Bitcoin, which is the most representative of this proof-of-work blockchain. And it's because this concept was developed in a non-resilient way. I mean, there's nothing wrong about it, basically, but it was based on the fact that the network only works correctly if there are less than 50%, if there are less than 51% of people wanting to bring the network down, meaning, or to take, profit from it. It's called the 51% attack. You can look it up. It's the specter of all these blockchain systems that are based on the proof of work. Well, it so happened that in reality, this happened several times. There's dozens of millions of dollars or euros that disappeared in the course of these attacks. The most devastating one is the flash attack. And so we started thinking, are there things that we can do from the resilience viewpoint to make these blockchain systems not perfect, but resilient? And actually, we came up with the first permissionless blockchain system that withstands way over 51% attacks. It withstands 60, 70, 80%. So the attackers can have even 80% of power. It's parametric. It's about robustness. So, and with this kind of resilience principle, of course, this is just to exemplify. These were emblematic, systems. Of course, Bitcoin, Bitcoin NG, Bitcoin, and we were the system that would cope with all the attacks, and one of them, of course, in a moderate way. All right. So, I hope to have convinced you that, it's always the same, it's separated with fall, united with stand. So it's looking at things from a systems perspective and understanding that this new paradigm that draws from existing bodies of knowledge, it's not just a collage, of course, this new paradigm is really creating a lot of promise to handle this very complex world that I was telling you about. And there are already research, successes, not just my group, several other groups in the world that really show that this is the way to go. Thank you very much, and I'll take questions.
Thank you very much, Professor, for your talk. So in the meantime, you can get your questions ready, and I'd like to start with one from the online ones. So it's an interesting one to me. Do you think there should be more knowledge on cybersecurity, and it should be taught in schools to help make people less vulnerable, or do you think this might cause more hackers and cyber attacks in the future? What's the ethical point of view you have?
Yeah, that's a very good question, because yes, not everything is technological. There's something called literacy, and so the cyber literacy in general, but also obviously the cybersecurity and dependability literacy is something quite important. So I am a true believer, and actually, in the countries where I've been, in Portugal, in Luxembourg, I've always gave all the help that was needed to bring this message. We would go to the talks, in high schools, Actually, high schools today is probably too late. I would say that in primary, the kids, actually, this reminds me, I wrote a paper I was already in Luxembourg, but I wrote a paper for a Portuguese magazine about what should be done with the kids, what should parents do with the kids to improve their literacy. And I had a lot of fun, and it got a lot of positive feedback, because you have to come up with parallel notions. I mean, I remember one of the passages of the paper as well. By the time, because when should we give a smartphone to the kid so that he can play, be on his own? And I said, well, I'm sorry, but you should only do that when you're ready to send your kid out to the town and get to school by bus alone. So when you think it's already time to do that, then it's time also to leave him or her navigate, alone on the internet, and things of the like. So yes, absolutely, that's what I've talked about, of course, was technical, but it's no use if the users don't understand what they're doing, really.
Any questions from the audience I can have? Don't be shy. I'll go on with one more online, and I'll take another in-person question next. So, interesting. What's your latest and greatest translational project in the kingdom? How do you think KSA can reach the level of digital sovereignty achieved by Estonia?
When? You mean when or how?
How?
How? Yeah, that's a very good question. So Estonia learned the hard way, right? There were, I wrote in a newspaper at that time, there were probably the target of the first open cyber weapons experiment. So when you have high emotions, then you trigger a path. I think it's not necessary for us. I hope won't be necessary for us in the kingdom to go through that path. I've been accompanying, the situation, meaning trying to understand what is the level of the culture and so on. There's something very, 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 enthusiastic about the evolution of the kingdom, which has to do with the use of technology. So that's amazing, because that's an opportunity. Now, we should not rush things. This maturity, it's actually called maturity. It's studied. You can study an organization and try to understand the level of maturity in cyber, generically speaking. This maturity does not, happen, for tomorrow. So my take to achieve this, digital sovereignty is that the kingdom must invest, and it's investing, of course, but keep investing on training, on high-level training of people that then go to the tissue and they make the transformation in the tissue. It's going to take some years. We have to be patient, but if we rush things, we risk failing. That's my message about that. That's a question.
Yes, please, Iman.
Thank you so much for a very interesting talk. My name is Iman Al-Haji, and I'm a PhD student in material science and engineering. As a non-specialized person in cybersecurity, I know very little. I tend to trust the system. I just trust everything around me, that it's going to work fine. But after I saw your touch on, for example, a Tesla or other things that might really affect my life, what would be the tips? Should I just keep trusting the system, or when an attack comes, I basically, my computer, I just shut the system. But what should I do, as a normal, a public person facing a cyber attack?
Thank you for the very honest, question. That was amazing, because there's nothing wrong with us trusting things. What must be done, and actually, technically, some of us, this network of excellence and resilience, it developed very good concepts on that line, which is we should trust something only up to the measure of its trustworthiness. So how about that? The question that you make is amazing because you're saying, I tend to trust everything. But that's what we want to do because we're in a society, we want to trust, everything that is available to us. Unfortunately, not everything is trustworthy. Trustworthy means deserving of our trust. How does this get then more technically? It's what we have to do is not be, stop trusting, no, it's be skeptical. Skepticism is one of the roots of knowledge, right? And so what you have to do is anytime someone tells you, for example, this is encrypted end-to-end, this communication is encrypted end-to-end, you're super safe. Well, research about that. You don't have to be, none of us has to be a specialist, in this area to understand how things are because, we go to the internet, we search stuff. We don't read the first thing that comes and believe it. But my advice to you is that anytime that you, should I trust this, or my smartphone bliss, or this my computer that, not being your area, of course, because we have other means. Just go try to know more and search for keywords like incidents, problems, whatever you're using, incidents, problems, trust. And that will help you progressively gain literacy in the more sophisticated use of things. Because, you see, those are the things that in a society are super important for what I was talking about, the digital sovereignty. Because digital sovereignty starts from the people, right? The people says, okay, so we feel like this. And so it needs, the people need to understand what is the problem so that they are, ready to require a certain level of sovereignty, which in your case is what you said is the key to that. If I don't trust this thing, I'm not sovereign about what is happening here. So I hope I helped, and feel free to mail me, in some months telling me, okay, I'm sorry, Professor Paulo, this doesn't work, or yes, it helped me.
Thank you so much.
So if you have other questions in person, please take up the mic. I'll go on with an interesting one. It's coming from Salim. What's the most dangerous cyber attack that you have ever encountered, and why it was so dangerous and how it has been prevented?
Okay. So maybe dangerous is a loaded word, but I'll tell you what was the most fascinating cyber attack that I've encountered, and I actually, we and colleagues, we really have looked at it, with a lot of attention. Was the attack, the Stuxnet, so the so-called Stuxnet, which was the attack on the Iranian centrifuge machines. Why was it, to some of us, amazing? Because actually, that attack had side effects that a lot of people probably don't know. That attack was generic enough to be used against a lot of other things. So you see, the fact that it was the Iranian centrifuges, for me, was irrelevant. There were turbines, conceptually, it could have been used, for example, to Siemens gas turbines that almost all the countries have as part of their electricity, the production system. The gas turbines are fast-triggering methods to produce energy. And so when, for example, the renewables are going down or, the market price is too heavy, they launch them. So all the countries have them. And so this is why it was so fascinating. It was not narrowband. And actually, you can look it up. It's called Stuxnet, with the U, Stuxnet. And actually, what was fascinating is that to some of us, we knew methods of attack, of course, because if you want to defend, you have to understand how things are attacked. And what was impressive was that it was a collection, a collection of methods to get to a point which was, in principle, in theory, inexpugnable. And that is, of course, dangerous only in the point that you think you're secure, but in the end you're not, right? Because it got to to one of the most difficult points to reach on Earth, if I could classify it that way. So to me, that was the most, I would say, fascinating cyber attack that I've studied. Yeah.
Thank you. I'll go on with some questions on the electrical vehicles. So do you believe that the EVs have been sufficiently tested and are safe to be deployed at such large numbers, given the fact that you talked about some cyber attacks on electrical vehicles?
Of what? Because this is making an echo, and I'm hearing your voice from two. Can you repeat the question?
Do you believe that the electrical vehicles have been sufficiently tested?
EVs, okay. Yeah.
And then is it safe to be deployed?
No. You know, if you're attentive, that's easy. If you look these kind of things up, you will see discussions. Some colleagues of mine that are part of my close community, they have been active on commenting about that, you know, on LinkedIn and on other venues. And the problem, as we are seeing now, is that, you know, there are some companies and countries that want fiercely to go ahead, and so you see more noise and looks more successful, so to speak. In other countries and other car makers, especially in Europe, that is very regulated, and thank God, I'm sorry to say, it looks like it's not so advanced, but it is, except that things make less noise. Exactly because the level of testing, you know, the threshold for the level of testing, I think it's much lower in the first set of countries than it is in the second set of countries. Now, this said, and so that you understand exactly what I'm talking about, I'm sure that those of you, not all of you, those of you who are really attentive, you saw that in one of the slides, I say, here is Tesla again trying to turn left against traffic. You know, this person, who is an engineer, had been testing it, and for the second time, Tesla wanted to turn left and collide frontally with the car. Now, if we go right Tesla, you were told, oh, but we never told you our cars are autonomous. And then you say, what? No, because it has to do with the semantics of levels. I don't want to bother. You can look it up. There's level 1, 2, 3, 4 automation. And so Tesla, the marketing of Tesla makes it look like, yeah, you can go, wow, you can watch a Harry Potter movie and then die, which happened, you know, some years ago. So this guy was watching a Harry Potter movie, and the Tesla collided with a truck. When the family tried to sue Tesla, Tesla said, we never said you could do that. No, they lead people into thinking. But you see, then it means that we're not there yet. Now, the recent cases, because of course, as you use it more, I would say that the only advantage, but it's a big advantage, let's put it frankly, of these countries that are more liberal in letting do experiments and you can drive and we waive your problems, they are showing that definitely we're not there yet. Now, why are we not there yet, in my opinion, now from my research group? Because we never will if we persist in the current paradigm, which is data level, so it's data level based. It's based on give me enough data and I'll move the world, like the metaphor of the levers. The way we're using, you know, deep learning networks to really tell you how to make, you know, the right recognition of images and then do trajectory plans. This is for the autonomous vehicles. Being exclusively, you know, at data level is not going to get us there. Why? Because any little thing that happens anew will not be seen by those algorithms. And then this is ultimately the cause of another death that happened with the Volvo. But the problem was not the Volvo algorithms. So Uber thought that the Volvo algorithms were you know, too paranoid, and then they changed them with some algorithms that their own team crafted, and they killed a woman. And the woman was, you know, crossing, you know, a zebra with the bike by hand, which is something that any human would have understood, right? But, you know, God knows why, you know, the Uber car, the Volvo car did not understand. So you see, I think that the research that I want to spawn here is, as I told you, for the right use of AI and ML especially, to get us to something that has an ultimate resource of trust to do something which can be in the car to stop it if something is really not matching what you're expecting. This has to do with research that has been done over the past maybe 10 years by some of us in distributed algorithms that really anchor your ultimate decision to something that really then, stops you or makes you get to a even if operational, to a safe stop. So the question is, we're not and we never will.
Thank you. So in addition to cybersecurity, hardware security, such as tampering, is also great importance. Why don't we see people talking about that much as cybersecurity?
Okay. I mean, preaching to the choir. I showed you some hardware level stuff, right? And actually, this is work that we've done in Luxembourg. Today in my group, I've hired, 2 excellent postdocs who work at this even lower level, hardware level. Because, so to tell that cybersecurity, it's generic. When we talk, hardware security is a part of cybersecurity, just to be clear about the terminology. But yes, that's a very good question. Yes, I think people, up to a certain point, believe too much that the problems at hardware level were solved. And there were, huge cries of alert recently, things called Spectre, Meltdown, Rowhammer. You can Google all these words, and I tackle more the distributed systems algorithms, but always I've been doing that for the past years, anchoring them on hardware that really, and that's a little bit unveiling what I was talking about AI. It's the same thing. Some hardware that anchors decisions so that they can be the ultimate resource of trust. Now. What we had done was, as you have seen at this chip level, we were working, for example, designing FPGAs. And I'm convinced that we have to go a little bit down. So whereas in my group we continue doing high-level algorithms, it's going to be funny because these algorithms will learn how to use some knowledge that is given by little tiny things in hardware that then we should design for them not to be attackable. Yes, that's definitely a very important point.
Lovely, thank you. And a technical one, do proof-of-stake algorithms more secure than proof of work, or are they similar?
Okay, that's a very good point. So the algorithms depend on how they're done. For example, the principle that we designed behind RepuCoin, although it was used for the proof of work, because of course this is where we thought we could get more impact, and we got surprise. It can be used with other paradigms. So the algorithm, the end thing, it depends on how it's done. The method, of course, proof of stake, I believe in it, not only as a researcher, but as a society member, because for me the future of cryptocurrencies and blockchain, oriented stuff is that they have to rely on something that is more material. The proof of stake, for those of you not so much aware, is that you have to show that you have a stake. So you have to show you have a responsibility for the success of the thing to gain then power to be part of the thing. So it's a more robust principle, definitely, yes.
Thank you. So actually I want to ask about the quantum computing, which has been mentioned, if you can comment. I understand that to advance and unleash its potential, lots of fault-tolerant qubits are required, right? And so how do you see the future will be? And once it's there, what will be the implications or challenges we will have?
Yeah. Okay, I always like this challenge and the questions. So to tell you, I'm not an expert on quantum computing. The second thing is that there are several, not many people understand this, there are several facets of quantum, okay? There's sheer quantum computing, there's quantum communication, there's quantum encryption and key management. And depending on that, the hardness of the later, for example, is not that much, so, but depending on what you want, so will be the hardness of solving the problem. My opinion is that for betting on generic quantum computing, it takes a lot of effort. For example, if a university is to tackle quantum computing, well, that's huge. That's a department per se, if you want, or something like that. Now, getting to fringes of quantum, that's a different thing. And so this is what we call post-quantum resilience. Actually, resilience, the name again, or post-quantum security. There are the two terms. And so to reach that, there is recent research, so you don't have to venture completely into quantum. I don't know if I'm being clear. One thing is, quantum is going to destroy, for example, asymmetric crypto. So we should research on, new forms of quantum bliss, quantum that. Why should we go there mandatorily? There's a huge body of research on classic crypto, and so maybe what we have to do is find out new mechanisms that are resilient against the advances of quantum, okay? But of course, it's not this I can opinate because this is what I feel can be done. Actually, an algorithm that we developed in Luxembourg for another thing was post-quantum secure. Now, for researching on quantum, I'm not seeing it happening that fast. There are things we keep saying it's for tomorrow, but I don't see it coming as fast for some of the reasons that the person in the audience was asking. There's a question there.
Thank you. Just a couple of minutes left, so I'll just pick the questions. What is your view on the resilience of AI-driven systems? Are AI being a black box and we mostly don't understand how it can go wrong?
Yeah, but that's the problem. So you see, so that's exactly the worry was that. So getting into a little bit of detail, those of you interested, I think you can search. So we organized the big AI conference some months ago. And I gave a talk there where I elaborated a little bit about that. So to be quick now, in some things that don't have a lot of requirements, AI is going to be and is super useful. But that's what the more soft things that will help you improve things, recommendation system and all that, okay? If you went to some more critical things, and critical things can be for society, so it could be about fake news and this kind of thing, I think that we still have to do better in research. Some of my colleagues in my area, they're creating a new area called dependable ML. So I think that explains exactly that, yes, we suffer that problem. So some colleagues of mine, I'm trying to bring one of them to give a talk here, maybe this year. They're researching on dependable ML exactly because we cannot afford mechanisms, some of the deep learning mechanisms, yes, we cannot explain them thoroughly. We just say, okay, it works. But this is not acceptable for the design of a car. That's the problem. It's not acceptable in Europe. It's acceptable in America. You cannot do a certification process, which is a bunch of paper where people sign their honor, their prestige, saying, oh, yeah, I don't know how this works, but I think it works well. I sign no way. So the explainability of AI is, most of the papers I've seen, explainability is a very fluffy term. If you are to really do explainable AI in the right rational mathematic term, we still have some way to go.
And I'll take the final question as an in-person one. Please go ahead.
Hello, Professor. It was a really nice talk. So my question is, when social media was coming, everyone thought it's a great idea. And of course, it's a great idea still now, but we can see that it has so many bad consequences we are facing, in our society. So when we are filling our life with this much AI, I know that AI cannot be avoided. It is the future. But when we are filling this much our life with full of AI, So are we at least taking the consequences in the account, like when we are doing this research and all? Like, I understand research ethics is now added, but the consequences, are we taking into account or not? Like, that is my question.
Yeah, absolutely. You see, that's a very good point when you say, things happen in our lives. And then, we thought it would be all for the good, but then there's a lot of bad things. It keeps happening, yes, absolutely. And so what we have to think is, okay, so how can we make this innovation, good enough or safe enough or workable enough and so on? And then, of course, I come from a very comfortable point. If I were only doing, AI, I might be worried, how am I going to handle this? But actually, because it's a lot to do, let me tell you, and this is something that was so clear for us in our group in Luxembourg, there is, to simplify, of course, there is the data level and the systems level. So, and if you just try to solve problems at the data level, just bits, in bytes and in words, and it's not going to work. Exactly from the points you were saying, from the predictability, from doing good things, be sure to tell you that they do good things. If you bring in what we call the system awareness, well, okay, so this works on computers. So how can we devise algorithms that, as we say, are system aware, and then you can get, much better results. Some of the results I've showed you came from this perspective. It's not any super rocket science. It's just saying, no. And so now, if you look at AI with the system perspective, this is why I told you I'm comfortable, because the things that I have now in my mind for the research that I want to do here in KAUST have a lot to do with this combination of the abstract data level and the system level. To be very clear about how powerful is this construct, I've had discussions with AI friends, over the past few years, and they will say, oh, no, I mean, this then requires, it's getting very slow, and so we should buy a faster GPU. What the hell is that? No, it's not about that. No, the thing that is below has to be typified and analyzed and theorized as much as what you're doing at the higher level. If you do that, then it comes to what you're saying. Then you say, okay, so this algorithm should never give me fake news, or should never, have unbalance or something like that. And you just don't pray. It's going to be something in the system that helps you achieve the objectives. Remember this, every one of you. Data does not compute. Computers compute. So we should not forget them. Thank you.
And that's a great quote to end this session. Thank you very much for all the questions, and also our speaker. And we'll go on with the web. Thanks again. Let's give it an applause.
Thank you very much.
Thank you. It was a pleasure.